Okay, now it's recording. I'm going to go ahead and share the screen. And as per the other review sessions, I'm going to be calling on people as well, or asking for volunteers to walk us through some of these problems, just because, I don't know, maybe did you guys find any benefit from that so far? Like, I'm trying to change some things up, so it's like, I guess you guys might be a little bit more involved in the homework. But I mean, like, I know this stuff, so it's like, I mean, I could sit around and just kind of explain it and go through it and on and on and on, parts A through H or whatever. But I mean, I thought it would be better to give you guys a chance to kind of work through it and then, you know, yeah. But did you guys find that beneficial last time for that probability chapter to kind of like get an opportunity to solve it on your own? Okay, fair enough. Hopefully we can continue that, and that'll be helpful for this chapter as well. But problem 1 is random motion of 100 particles. A scientist is measuring the random motion of 100 small particles in a long, very thin tube with the aid of time-lapse photography. She locates all the particles at a given time and again 20 seconds later. She measures the displacements all in the positive or the negative x direction and counts the number of particles that travel different distances from their starting points. Motion in one direction is arbitrarily called negative, and in the opposite direction, positive. Following table is obtained. So you have, this is very similar to that problem from last week's written homework as well, where we have these different probabilities, different displacements, right? I think it's actually pretty much identical, that same table there. But we have 100 small particles basically. So for part A, it is saying it's most likely to find a particle at the original position at a displacement of 0, right? And when they say this, right, there's a distinction made. I don't know if you guys covered this in class or if you watch the online lectures that Dr. DeJong has, if you're in his section. But generally, right, if you run a bunch of trials, if you have a bunch of particles, we have a like infinite number of time steps or infinite number of particles or whatever, then things will average out to be 0 at the end. So like you're most likely to find a particle at a displacement of 0 if you have so many trials, right? But if you only have a finite number of trials or a finite number of particles, the average displacement, right, your average displacement will be approximately 0. It won't be exactly 0 if it's a finite number of trials or particles or whatever. The only distinction there is that even if they have a finite number of particles or whatever, then what they'll say, for example, in a problem is that they'll say like, oh, it's a simple random walk. So if it's a simple random walk, then you know at that point that your average displacement is going to be 0. So you can stick with that as your average displacement in that case. But yeah, that would be the other situation where you'd have that. Otherwise, just keep that in mind just from a conceptual standpoint, because that might be a multiple choice problem, for example, on the exam, is that when you're doing simple random walk or you have like infinite number of trials or infinite number of particles or whatever, your average displacement is going to be 0. But if you have a finite number and they don't say it's a simple random walk, then your average displacement will be very close to 0, but not exactly 0. But yeah, I figured I'd clear that up from a conceptual standpoint. It says it's also just as likely to find a particle at some positive displacement as at the same negative displacement. Probability symmetric around 0 displacement, right? We see that bell curve. That's what we see. So we have 0 in the middle there, right? Yeah, this is negative step size here, positive step size. And so they'll have the same, relatively the same probability, be mostly symmetric. And you can see that here, right? If you have positive 10 is 0.23, negative 10 is 0.23, right? And so on. The motion of a single particle is very similar to a 1D random walk. So there we go. That's the condition there. Use this to explain why these two features of the probability table make sense. So they're asking you to basically explain why it makes sense for there to be a displacement of 0, I think. Yeah, displacement of 0. And that it's, and then that there's a symmetric kind of distribution there that we have. So why is that? What about a simple random walk, helps you determine those two conditions, that there's a displacement of 0, or average displacement of 0, and a symmetric kind of distribution. Anyone want to give it a shot? I technically already kind of gave the answer for one of them in terms of at least like the average displacement part. Yep. So simple random walk. So actually, let me, you know what, because this is an explanation type problem. There's not like an equation that you have to use or anything like that. So let me type this out. So, okay, hold up. There we go. Since this is a simple random walk, right? Over a long period of time or extended number of trials, right? Oops, trials. Or time steps. I kind of said this earlier, right? The average position is going to be back where the particle started, right? So they started at 0. So it would make sense for a simple random walk that the average displacement, the average position, is going to be back where the particle started at 0. And that's where we find the highest probability, right? That's why you see here at 0, it's 0.4 compared to the others. So because they, oh, am I frozen? Hold up. All right, let me go back to that real quick. There we go. So is that better now? Can you guys see that? Okay, cool. Yeah, so because, like Zainab said, there's a simple random walk kind of condition there, it means that over a long period of time, extended number of trials or time steps, the average position or displacement is going to be back where the particle started at 0, and that is also where we see our highest probability, right? It's most likely that the approximate displacement is going to be 0. So I'd even include that reference to the table there, that you say that the highest probability, 0.4, is found where the approximate displacement is 0 micrometers. So I'd relate it back to the table if you can as well. Now, the second thing that we observe, right, is the symmetric distribution, right? Why do we see the symmetric distribution? Other than the fact that, like, I mean, in a simple random walk, yes, you have a symmetric distribution. But why is that? Why is it in a simple random walk you have a relatively symmetric distribution? Yep, excellent. That's perfect. Yep, that's perfectly right. Yep. So because in a simple random walk model, right, the step of one molecule is not affected by another. And so moving negative x, moving positive x, right, there's an equal probability of moving left to right, basically, right? And so that's why the probability distribution is kind of, they're mirror images of each other, like either side is a mirror image. So because of the simple random walk model, right, steps left or right will have an equal probability of occurring, right? So the step of one molecule is not, is it frozen again? It's probably because I'm typing fast. Hold up. Yeah. I'm too quick for Zoom. So step one of the step of one molecule is not affected by the step of another molecule, right? And so moving in the negative or positive x direction would have an equal probability of occurring. That's why we observe a probability distribution that mirrors itself on either side, producing a bell curve. And I would make sure to mention the bell curve kind of idea there. So hopefully that didn't freeze again. It's lagging again? Okay, hold up. I got it. Yeah, no, I just go in when I'm typing, and so like I have total disregard for the lagging. But hopefully you guys can see that there. Like that's. But yeah, both explanations are absolutely right. Because it's a simple random walk over an extended number of trials or time steps, average position or displacement is going to be back where we started at 0. That's where we find, incidentally, the highest probability as well. And also because the simple random walk model, steps left to right will have an equal probability. Step of one molecule isn't affected by another. And so you'll see a probability distribution that has like a mirror image on either side, and that's our bell curve, right? So that's part A. Now, let me detach the keyboard here, move back to the pen. All right, so that's part A. Hopefully that makes sense. But part B now, it says, given that there are 100 particles, how many do we expect to find at a displacement of negative 20 micrometers? So if we have 100 particles, right? And remember how this thing is set up. I'm going to give you a hint as to how this is set up here. So like on a histogram, right? Or, you know, whatever kind of graph you have. But generally, yeah, histogram. You'll have like maybe the displacement here. Let's say this is 0, this is negative 10, this is negative or positive 10, positive 20, negative 20, right? And then you have like your probabilities here. And so if we don't have like probability per se, we might say like we have, this is like number of particles, right? So you can say that maybe there's 3 particles here, 5 particles there or something, 10, whatever, and so on, right? So the thing is now we have probabilities for these, right? And we have these, right? If we wanted to say like these were, there's 3 particles here, right? And 3 particles out of 100, for example, that's okay, that's 0.03, right? If we had the number of particles here on our y-axis. Now they're giving us the probability automatically. So if they were to take this away, it's frozen again? Okay. My gosh, I'm sorry. All right, let me share that again. There we go. Thanks for letting me know. I just like look down and I forget to look up at the chat. Yeah, so instead of giving us like number of particles here on the side, they could also give us probability as well, right? So if you have your probability, you could say, for example, then that probability of being at negative 20 is a probability of 0.06. Well, if I have 100 particles, right, when I say there's a 6% chance, right, 6% chance of what? Okay, there's a 6% chance of finding particles, or 6% of particles essentially will be found at approximately negative 20, right? So with that kind of hint there for B, anyone want to suggest how we can figure out the number of particles that we can expect to find at a displacement of negative 20 micrometers? Yep, exactly. 100 particles times probability at negative 20 micrometers, that's 0.06, right? And so that gives us 6 particles, right? We expect to find 6 particles, 6% of the 100 particles, right, at a displacement of negative 20 micrometers. So that's part B. Am I lagging again? Okay, cool. Yeah, the Wi-Fi is not it today. That doesn't bode well for the upload speed later on. But yep. Yeah, for the histogram idea, it's just like if you have your probabilities there on the y-axis, then you take that probability, right? Oh, I'm not writing, dog. Oh, I am. Are you serious? It's frozen even when I'm scrolling up? That's bogus. All right. This is what a wonderful night. All right. There we go. All right. Hopefully you can see the histogram there. But yeah, you just take the probability times the number of particles that'll get, because the probability is giving you the like percentage of the particles that will be found at that specific displacement. But yeah. So for part C now, they want us to determine the mean displacement of all 100 particles after this 20-second time interval, right? So remember, mean just means average, right? And so if they're asking us for the average displacement of all 100 particles, they're asking for x with the brackets there, right? Your average. So remember, yep, go ahead. Yep. Mm-hmm. Yep, exactly. Yep, exactly. And it's going to be, if we were to set it up as an equation, right, we can say that it's the sum of each little displacement times the probability of each displacement, right? We sum up each displacement times the probability of finding particles at that specific displacement, right? So we can then say that, okay, well, there's a 0.01 probability at, actually, let me write it in that form. So it goes value, then the probability. So we have negative 30 micrometers, and there's a probability of finding particles that displacement of 0.01, right? Yep. Am I frozen again? This is wonderful. All right. All right. I would consider switching over to my hotspot, but I mean, I don't know. Well, if I end the meeting, actually, yeah, I could end the meeting because the recording is separate from the meeting. It's not through Zoom, but um, I don't know. That would probably be a pain for most people. But even then, like, it's just the Wi-Fi that's just bogus tonight. One sec. Let me try and just like switch over to my hotspot or something. But I doubt that's gonna help with the speeds because I know for a fact my hotspot is not gonna be fast. Um, honestly, like, we'll probably just have to like carry through, and then the recording will be up, and the recording's flawless. Like, it's a screen recording via USB. So, but hopefully you guys can at least like hear and understand what I'm talking about to a certain extent. And I'll just keep me updated on whether it's frozen or not, because there's just some nights. But we take the value negative 30 micrometers, right? Multiply by the probability, which is 0.01. And then we add that to the negative 20 micrometer value times its probability, right? And that was 0.06 plus negative 10 micrometers, and that was 0.23 plus 0 micrometers, and that's 0.4, so that ends up being 0 anyway. Then we do that again, basically. Oops, not 0.23. Lagging again? Okay, thanks. There we go. Plus another 10 micrometers times 0.23 plus 20 micrometers times 0.06 plus 30 micrometers, and that's times 0.01, right? So once you sum up all those values, then you should get somewhere around 0, right? That makes sense, and that's a sanity check right there, because why? This was deemed to be a simple random walk model, right? And so it only makes sense then that our average displacement of all the particles, because it is a simple random walk, should be 0, right? So I would still go through the motions of like solving it out like this, just so you can show that. Maybe alternatively, you could just say that since it is a simple random walk, that the average displacement would be at 0, but it's just safer to go ahead and like calculate out the mean like that. But yeah. And I think even in the answer key, I'm pretty sure they want you to calculate it out like this. But that's the mean displacement of all the 100 particles, right? Now they want us to figure out the mean square displacement. So mean squared, what is that? What is the mean squared? Excellent, yeah, so take all those values that we have here, right? Basically do the same thing, except square every single value. So negative 20 squared, negative 10 squared, 0 squared, 10 squared, 20 squared, 30 squared, and so on, right? And that's this value here, which is the x squared with the exponent on the inside of the brackets, right? That's what I was talking about the last chapter. So that's the same as taking all of this, right? Copy, paste, and then squaring everything here. Take every single value, square it, and then multiply it by its probability, right? And that's the same as taking, if we were to write it as an equation, oops, I don't want to cut, I want to copy and then paste. So if we were to write this as an equation, right, it'd be xi squared, right? You take every single value, square it, then multiply by the probability. And so then that should give us around 112. Lagging again? Okay, 1 sec. There we go. So that should give us 112 micrometers, and that should be squared as well. Which is kind of odd because, you know, that sounds more like area than a displacement, right? But since all of these values are squared, the units are micrometers squared. And they're asking for mean squared displacement, so you expect to see a squared there. But yeah. Sound good so far? Okay, for E now, determine the root mean square displacement. Right? Let me, anybody else want to give this one a shot? So Matthew, you've spoken up. Zainab, you've spoken up. Anybody else want to give this one a shot? Okay, go ahead, Christian. Yep, excellent. So, yeah, go ahead. 10.6, yep. So x RMS is the root mean square displacement, right? And that's going to be the square root of our mean square displacement. So root mean square displacement, think root of your mean square displacement. So x RMS, root mean square displacement, it's the square root of your mean square displacement. And your mean square displacement is the x squared with the exponent on the inside of the brackets. So it'd be like this, right? So essentially we just take the square root of this value, right? So square root of 112 micrometers squared should just give us around 10.6 micrometers, right? Excellent. But yeah, that's the root mean squared displacement. Now for F, how does the root mean squared displacement compare with the standard deviation in this experiment? So how does XRMS compare to the standard deviation? Let me see here. Okay, I'll pick on someone this time. How about Eric? Eric, I think you like unmuted with Christian at the same time, so I'll give you a chance to do this one. Mm-hmm. So let's start with the equation first, right? So do you know the equation for the standard deviation? Yep, like that. So if we have, this is our mean squared displacement, right? And then this would be like our average, and then we square it. So if our average is 0, right? Exactly. So it is equal to our root mean squared. So we should see then if this is 0, right, then our standard deviation should just equal the square root of our mean squared displacement. And so this is the same as our RMS. So you can kind of write that out, right, and say that, well, this is equal to standard dev, and that's equal to x RMS, right? So since our average is 0, standard deviation is equal to the root mean squared displacement. Make sense? Cool. Now, we have to determine for part G the diffusion constant, right? So this, right, you're going to have to notice that, well, we've been talking about root mean squared displacement, and now all of a sudden we're jumping to diffusion constant. Well, how do we relate the two? Anybody want to give that a shot? Yep, go ahead. Mm-hmm. So squared over. Yeah. So like this one. So now here's my question, right? Actually, hold up. No, I don't have a question. I was about to ask something totally different, but no, this is right. And this, right, if we wanted to kind of rearrange things around, right, and think about it, well, there's also this equation that's direct. If people are unfamiliar with the, this is the step size. V squared times over 2. Yeah, and this is absolutely right. And then there's this third equation here, which is the root mean squared displacement is equal to the square root of 2 times the diffusion constant times time. And these are all valid, right? The only issue here is that, for example, that v squared, well, we don't know the speed, so we can't really use that one. But we could use the step size squared divided by 2 times the time, right? So we have the time. That was 20 seconds, right? That was hidden in the problem very early on, 20 seconds later, right? That's our time. Now our step size, right? And this is, when we think about this for our step size, right, it should kind of be our, because we're assuming for a simple random walk and stuff like that, it's all of these particles moving together. When you have diffusion, you label things right, or you think in terms of all of the particles moving together at once. And so with diffusion, they're all together moving at once towards a specific region, and that specific region, we define that as the XRMS, right? So this step size here in terms of diffusion, when we're looking at diffusion, it's the XRMS here, right? And so we can simply just take the step size, right, which is the XRMS, 10.6 micrometers, and then square that divided by 2 times our time, which was 20 seconds. And that gives us 2.8 micrometers squared per second, right? That would be our diffusion constant. That's if we used this equation, right? You could also, just to kind of like visualize it a little bit better, without thinking about like step size and relating it to diffusion necessarily, you could also just think about it directly with this equation, which is the XRMS is equal to the square root of 2 dt. So if we have our XRMS, right, that was the 10.6, we want to take the square of both sides, right? XRMS squared, that gets rid of the square root, so you're left with 2 dt. And if we want to figure out the diffusion constant, we just divide over 2t, right? So in the end, you have d is equal to XRMS squared over 2t, right? So your t is 20 seconds, XRMS is 10.6. Square that, divide by t. But yeah, t is the 20 seconds, remember? Because then earlier in the problem, they said with the aid of time-lapse photography, she locates all the particles at a given time, and again 20 seconds later. So they had like 20 seconds to move. Yeah, go ahead. So, because I think in the beginning of the problem they said it's very similar to a 1D random walk. Mm-hmm. Yeah, normally if we were just talking about particles and they didn't like specify what's going on necessarily, then yeah, it would be like normally it'd actually just be like 3D if you have like a gas or something like that. But like they'll like give you either information or a hint as to what's going on specifically. So like here they told us that it's very similar to a 1D random walk. So we assume that everything is going to be 1D, and especially since they said here motion in one direction, so they only have positive x or negative x, right? She says that she measured the displacements all in the positive or negative x direction, so that's only one direction, 1D motion, right? Otherwise, like if we go into another one of these problems here, like there might be an indication as to, a different type of movement, right? Either 2D or 3D, depending on what's going on. And we can assume, I think, for something like, let's see here. So if we go to problem 2, for example, how long would it take for a large number of sodium ions to diffuse inside the amoeba so that their RMS displacement 500 micrometers? Well, the amoeba are spherical, right? And if we're thinking about like particle motion diffusion, right, these particles are moving inside, outside of cells. They can move positive x, negative x, right? Move upwards, downwards, right? So, no, I was just explaining as to why we use 1D motion instead of like 2D or 3D. But I'm going to get to H here in a sec. But yeah, I mean, this one for C, for example, you'd use 3D because we're assuming the sphere is like kind of moving in all like, it's either moving into or out of the cell, upwards, downwards, right, in a vessel, for example. And then like, I was like, you can kind of say like into or out of the page. That's kind of weird, but like there's just 3D motion obviously because that particle is kind of moving in all directions, right? We're assuming that we can blow this particle, right? We can see it. We can look at all the different sodium ions, and then we can see it kind of moves all in different directions. But if we're looking about like particles moving in a biological sense, if there's a biological context like this, then it's 3D. It's safe to assume that it's 3D. Otherwise, if it's 1D or if it's 2D specifically, 2D is where it gets kind of weird because then they'll specify exactly like what's going on and if it's 2D or not. But yeah, I mean, I honestly wouldn't worry about like identifying if it's 1D, 2D, or 3D, because they'll usually do a pretty good job about either telling you that it's 1D or 2D or 3D, or just by the nature of the context of the problem, right? Like if it's a particle in a biological context, then we know those particles move like everywhere, right? So if they're moving everywhere like that, then it only makes sense for it to be in 3D motion. But otherwise, most problems are going to be 1D, I think. But yeah, you might see like a 3D one just because of like the biological context of this course. But the 2D stuff, like I'm pretty sure they'll just tell you if it's 2D or not. But yeah, sound good? But yeah, that's the diffusion constant for G. Now for H, we have some more explanation here for H. So it says at a later time, the probabilities of the particle's displacements are remeasured, though the new values are not given. So probabilities of displacement are remeasured, new values are not given. Conceptually describe how the following quantities would change compared to the values from 20 seconds above. For example, would they increase, decrease, or remain the same? So we don't have access to the probabilities necessarily, right? But from a conceptual standpoint, we can kind of predict what's going to happen to each of these different values. If they're going to decrease, increase, or remain the same with an additional 20 seconds. So as time increases, right, as time progresses, how does the root mean square displacement change? How does the location of the peak of the distribution, change? How does the width of the distribution change? But yeah. This was more like just if you kind of were there in lecture, or if you just watched the lecture recordings for Dr. De Jong, then this should be pretty easy. But anyone want to give a shot for number 1 here, part 1, the root mean square displacement, what's going to happen to it? Yep, go ahead. Mm-hmm. Yep. So root mean square displacement will increase with time, and then you can also, if you wanted to, you can also relate it to the equation, right? Because we know that the root mean squared here is equal to the square root of 2 times the diffusion constant times time. So as you increase in time, right, as you progress along in time, right, you're going to see that there's an increase in the root mean square displacement. So the root mean square displacement will increase. As soon as I start typing, it freezes. All right, hold up. All right, well, it's probably going to freeze again, so just like fair warning, I guess, because I guess I just type fast that it can't keep up. I don't know. But root mean square displacement will increase with time. I'll just type slowly then, just to keep it steady. So the particles move outward with time. So I'm like typing as slow as I can. All right, darn. Okay, so particles move outward with time. So time steps increase, and the root mean squared, I'll just say the RMS will increase. And then at the same time, right, since we know that the XRMS is equal to the distribution or standard deviation of the particles, then as the okay, so this is actually I'd actually leave this part out, to be honest, because it kind of answers part 3 a little bit early. All right, one sec. Hold up. Let me stop sharing and then share again. So for number one here, like I would actually maybe leave out the standard deviation part because it factors in. But what you're saying is absolutely correct because as you go on with time, the particles will tend to move outwards, right, from the center, and so the width of the distribution will increase. And so since we know that the width of the distribution in this case is equal to the root mean squared, if the width of the distribution or the standard deviation increases, then the root mean squared displacement would increase. But I think maybe that kind of factors in number three before we even get to it. So maybe I would just leave this like the width part or the standard deviation part till the end. But it doesn't matter honestly. Like you could, that's what I would prefer. I would just prefer to describe it from a stance that since there's an increase in time steps and x RMS is equal to root 2 dt, which t is time steps, right? Then as you increase time steps, the RMS will increase, the x RMS will increase. But what you said is also perfectly right because as you spread out over time, or as the particles get more time to move, they'll spread out even more. Distribution will increase. If distribution increases, or the width of the distribution increases, then your standard dev increases. And since we had already figured out that standard dev just so happens to be equal to the XRMS, then an increase in standard dev or the width will also mean an increase for the root mean square displacement. But I would personally prefer to just leave it at like the increase in time steps will increase. Yeah, the increase in time steps will increase the XRMS. But this also brings us to three. Yeah, go ahead. Yeah, yeah, yeah. Yeah, yeah. If you have it there, then yeah, just leave it. And then if you don't have this part though, that the as the time steps increase, the RMS will increase. I would add this part maybe just to kind of relate it back to the equation as well. But yeah, you can leave the standard dev part. I don't know if you have space to add it, but um, yeah. But yeah, for this part as well, the width of distributions, we know that. Well, I guess let me edit this part because I already kind of said it in the context of the first one. But um, for the width of the distribution, right, as time progresses, more particles will move outward. And so the RMS will increase. Yep, and so since the RMS happens to be equal or is equal to the width distribution of the standard deviation, then the width will also increase, right? And so you can also maybe say that, like, in a sense, this is something like straight from the lecture slides, I'm pretty sure, like over time as well, like this, I'll just add this as a notation here. So over time, particles will move outward. Oh, go ahead, sorry. It's frozen? Okay. So yeah, over time, particles will move outward, and then that will decrease the height of the peaks in the distribution, and the width will increase. That's at least from like just a graphical analysis sense, right? I have so much patience that this thing is cutting out. Yeah, I mean, like, I'm, yeah, I'd say I'm probably one of the most patient people when it comes to like technology. I'm the most patient and most impatient at the same time. It's weird, but um, yeah, no, I've like worked with technology all my life, so and I love it very much, but I've just gotten used to it not working the way it should be, like 90% of the time. So, but yeah, even like I don't know if you see, like you probably noticed maybe like when I'm using GoodNotes, it'll like show that the iCloud storage is like done, and I'm just like I don't want to pay for an extra like 5 gigs. Like I'm fine with the 5 gigs that I have. I'm not paying like $2 or $3 a month or whatever it is to get more iCloud storage. But I don't know. there's an error that keeps popping up and it's annoying, but it is what it is. Anyway, what was I saying? With a distribution, I think that's what it was. Yeah. So from a graphical analysis perspective, you can just say that as well. Like particles will move outward. That'll decrease the height of the peaks, right? Because you're less likely to find particles near the center as you go, over time. They're more likely then to be found, or like the likeliness of finding particles that are more outward, right, will increase over time because they're spreading out more. You're giving them more opportunities or more time to spread outwards. So that'll decrease the height of the peaks of each peak in the center, and increase the height of the peaks like outwards, right? And so the width of the distribution will increase as well. So I think there's like, maybe if I, hold up, let me jump over here and see. Okay, whatever. There's like a specific, yeah, that's the error that I was talking about. Not enough iCloud storage. We don't care. There. So I think this is the one. Maybe. Hold up. Hold up. I think that, yeah, that just might be, yeah. As time passes, the particles are more and more likely to be found farther and farther from the origin, right? So this would be like, I don't know, 20 seconds. This might be 40 seconds. This might be 60 seconds. You can see that the peaks in the middle will kind of decrease in their height over time, while the ones outwards right here, like for example, the ones outwards here, will tend to increase over time, right? So you go from a really like high curve like this to a more spread out one like that. All right, okay. Now I'm getting angry. All right. So, yeah, I was just saying that you have a really high bell curve like this, and then over time it kind of spreads out even more. So that's at least from a graphical standpoint as well, that you can kind of look at that. But then for number 2 here, location of the peak of the distribution. Does that increase, decrease, or stay the same? The location of the peak. So remember we said before that the peak, right, where we are most likely to find particles would be at 0 micrometers, right? That makes sense because in a simple random walk model, like we said earlier for part A, that we're most likely to find the particles at 0 back where they started, right? That's the highest probability of 0.4. So with time, does the location of that peak change? Does it increase, right? Decrease, or what happens? Stay the same, right? Because I mean, it's still a simple random walk model. So as you increase with time, particles will still most likely to be found at around x equals 0, which is the average position. So location of the peak will remain the same with time. So with time, particles still will be found at approximately x equals 0, which is the average position, because this is still a simple random walk model. Yep. Okay. 1 sec. Now I'm good? Okay, hold up. There we go. So location of the peak will remain the same with time. With time, the particles will still be found at approximately x equals 0, which is the average position, because this is still a simple random walk model. Make sense? I think that's all of problem 1. It's just a lot of parts, but like the steps to do them aren't bad. Problem 2 now is where we get into some of this diffusion flux stuff. But for problem 2, it's cellular diffusion. An amoeba is a single-celled organism approximately spherical with a diameter of about 500 micrometers across. So diameter is 500 micrometers, right? And then radius would be 250. Is it frozen still? All right, 1 second. There we go. An amoeba can ingest molecules by taking them in through the cell wall. Suppose an amoeba takes in a large quantity of sodium ions with a mass of 23 Daltons, 23 grams per mole, and a radius of 100 picometers, while at a temperature of 310 Kelvin. So T is 310 Kelvin, right? The intracellular fluid of an amoeba has a viscosity of 1 millipascal seconds, similar to water. So they're giving us values like temperature, viscosity. They're even giving us values of like the radius and stuff, right? So what was I going to say? Oh yeah. So judging by these values, we can kind of look forward a little bit and think, well, for example, for part B, if they were to ask us to figure out the diffusion constant, D, this is jumping ahead a little bit, but this is kind of practicing noticing how to extract like information from the problem. So you see values like temperature, the radius, right? Viscosity. How do you think we're going to be able to calculate the diffusion constant for B then? Because this is good practice in terms of like being able to extract information from the problems and relating them to an equation that you can use. Yep, excellent. So diffusion constant is equal to Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin, times the temperature in Kelvin, divided by 6 pi times the viscosity in Pascal seconds. So we have to convert them from millipascal seconds to Pascal seconds, and then times the radius, right? And that's the radius not of the amoeba itself, right? Because we're going to be calculating the radius of or looking at the radius of the particle that's moving, right? That's doing the motion itself, that's diffusing, which are the sodium ions, and they have a radius of 100 picometers. So you don't use this radius or this radius here, right? You use the radius of the particles that are diffusing. So be careful not to make that mistake. But that moved ahead. But now we're back to A, which is what is the RMS speed of these sodium ions, right? What is the RMS speed? So this kind of takes us back to last week's stuff, because if you think about RMS speed, well, there's two ways of kind of going about figuring out. Right? So in terms of like the probability perspective, right, we know that the VRMS is equal to the mean squared, or VRMS is equal to the square root of the mean squared like speed, right? So we don't have a way of figuring this out, right? Because this would mean like taking each probability value, squaring it, and then multiply by the probability of, having a particle at that speed. So we can't figure that out in terms of this equation here. However, we do know, right, that the RMS speed is included in another equation that can also be related to temperature. So we have temperature and we have speed. Now, how are temperature and speed related in a very general, broad sense of the term? Or at least, how do we define temperature? Part A, yeah. So yeah, that's perfect. That's excellent. That's exactly what we're supposed to do. Kind of jumped the gun there, but that's absolutely right. Now, to explain kind of why we go through this equation, the average kinetic energy is equal to 3 halves kBt is equal to half mv squared, where the v here is the VRMS, right? The reason why we're using this, and Zahra already posted in the chat, right? It's because I was asking, what is the definition of temperature, right? So broadly, right, definition of temperature is the average kinetic energy, right? The if we say there's a specific temperature, right? If we say there's something at 300 Kelvin or whatever, right? Then we're describing the average kinetic energy of a group of particles, right? So for the average kinetic energy of a group of particles, right, that's equal to 3 halves times the Boltzmann's constant times the temperature. It's also equal to half mv squared, where v is the VRMS, the root mean squared speed, right? The RMS speed. And so this is how we can relate the temperature stuff that we have here, right, to the speed, because we know that temperature, right, this is the way to think about this stuff. Temperature, right, the way that we define temperature is that it's the average kinetic energy of a group of particles, or it's related to the average kinetic energy of a group of particles, right? So we know that average kinetic energy, then we can say, okay, well, how do we relate average kinetic energy then to temperature in terms of the equations? Well, there's 3 halves kBt, and we also know that's half mv squared. So that's the VRMS squared. So it's VRMS and then we square it. And so that's, if you think about it, right, since I said earlier that the VRMS is equal to the square root of the mean squared speed, right? If we were to take the square of both sides, we can see that VRMS squared is equal to the mean squared speed there with the exponent on the inside of the brackets. And so if you actually refer back to your equation sheet, you won't see this being labeled as VRMS. What you'll see is it being labeled as half mv squared like this. You'll see it like that. And so then you know that, well, this is equal to the VRMS squared, right? So now we're just trying to figure out what the RMS speed is, right? So if we know that this is the VRMS squared, right, then we can just solve for the VRMS, right? So we know that the VRMS, and if you remember from like Gen Chem 2, I think, there's like just a very quick way to get through all of this, and that's just root 3 kBt over m. So that's after doing everything, but basically the way to get that is you multiply it over 2 here. So 2 times 3 over 2, the 2's cancel out, so you're left with 3 kBt, right? 3 kBt. Once you have 3 kBt, you can then divide over the m. Once you divide over the m, like there, you'll have the VRMS squared left. If you take the square root of both sides, if this is VRMS squared, take the square root, then you're left with VRMS is equal to the square root of 3 kBt over m. And so now it's just a matter of like plugging things in, right? So we know that this is root 3 times kBt. Kb is 1.38 times 10 to the negative 23 joules per Kelvin. Temperature is 310 Kelvin, right? And then we need to figure out our mass, right? So they told us that the mass of the sodium ions is 23 grams per mole, right? When we're using the mass here in this equation, it refers to the mass per particle. When you're using this mass here in this equation, it's the mass per particle, right? So this is the mass per mole. How can we get to the mass per particle? Yep, exactly. We use Avogadro's number. So we go from 23 grams per mole to 1 mole is 6.022 times 10 to the 23rd particles, right? Or ions or whatever. And then at the same time, remember that everything has to be in SI units. So we can't have grams, we have to have kilograms, right? So there are 1,000 grams in 1,000 grams in 1 kilogram, right? So if you do this part right here, that should give you your mass per particle, right? And this was around like 3.82 times 10 to the negative 26 kilograms per particle once you do that. So then you're left with 3.82 times 10 to the negative 26 kilograms per particle there, or ion, right? Either way. So once you solve that out, you should get around 579, 580, something like that. Yeah, I got 579.68 meters per second for my VRMS there. Sound good for A? Yeah, for this equation here, the mass that you use is the kilograms per particle. And even the same thing for this equation up here, right? For half mv squared, it's the mass per particle. Yeah, so 1 Dalton is equal to 1 gram per mole. And so then you have to convert it to kilograms per mole in terms of these equations here. Because remember, everything is in SI units here. This is like, when you delve here, it's in the chem realm, and so nothing in chemistry like deals with, well, I don't say nothing, but like, I guess like grams per mole is the molar mass, right? And so that's like the standard unit that we use for molar mass in chemistry, but that has no like, I guess, I don't know what the word is to use, but basically like we have to make up for that issue there with the SI units, because we know that this is grams, right? We have to convert it to kilograms to make sure that things are SI units for physics. Otherwise, as well, for moles, we have to convert it to particles, because if we're talking about average kinetic energy for molecules or particles or whatever, then we have to include the mass per particle. So kilograms per particle is what we're trying to get at. But yeah. So hopefully that makes sense for part A. Part B, we already kind of stated that earlier. That's the diffusion constant, and that's equal to the Boltzmann's constant times the temperature divided by 6 pi times the viscosity times the radius, right? And so remember, the radius here isn't the radius of the amoeba, it's the radius of the sodium ions that are doing the diffusing themselves, right? So your Boltzmann's constant is 1.38 times 10 to the negative 23rd joules per Kelvin. Your temperature is 310 Kelvin. We divide by 6 pi times the viscosity. Now remember, the viscosity is 1 millipascal seconds, right? And that's just the same as, if that was for 1 millipascal, right? That would be 0.001 pascal seconds. That would just be moving the decimal point 3 places back. Because remember, in 1 kilogram, for example, 1,000 grams, right? And so in 1 gram, there's 1,000 milligrams. And so if you wanted to convert from millipascals to pascals, it'd be kind of the same concept, right? So if we go from 1 millipascal seconds, right, then we know that or at least in 1 Pascal, right, we have 1,000 millipascals, right? So you just divide by 1,000 to get the number of Pascal seconds, right? Otherwise, if we had, for example, like kilopascals, then we'd have to do an additional conversion there as well. But you just divide by 1,000 to get the Pascal seconds, and then you also have the radius there, which is the 100 picometers. And so remember, deci, centi, milli, micro, nano, pico. And so that would be like 100 times 10 to the negative 12. Yeah, deci, centi. 1, 2, 3, 6, 9, 12. Yeah, decicenti, milli, micro, nano, pico. Yeah. 100 times 10 to the negative 12 meters. And so that should give you around 2.27, I think, times 10 to the negative 9 meters squared per second. Remember, diffusion constant, the units are meters squared per second. But yeah. Sound good for part B? Any questions at all? And for 100 picometers, because I know some people might have issue with this part right here, 100 picometers, I just do like, I know that 1 picometer is 10 to the negative 12 meters, right? So if I just take 100 times the 10 negative 12, then that's how I get the number of meters there. But 100 picometers is also the same as saying 1 times 10 to the negative 10 meters. So if we want to keep it in proper scientific notation, it's 1 times 10 to the negative 10 meters. That's the same as 100 times 10 to the negative 12, right? Because if you just move over 2 decimal points, then this drops down to negative 10 instead of negative 12. But yeah. Part C, then, is how long would it take for a large number of sodium ions to diffuse inside the amoeba so that their RMS displacement is 500 micrometers. So how long means that we're figuring out the time, right? Figuring out how long does it take for a large number of those sodium ions to diffuse inside the amoeba so that the RMS displacement is 500 micrometers. So they're giving us that the XRMS is 500 micrometers. We want to figure out what the time is to cover that RMS displacement, right? Now, how do we figure out the time? How do we relate time and XRMS? Yes, so in this problem here, XRMS, since it's just sodium ions and this is a biological context, like I said earlier, and then I think Medina, you were asking this question. I don't know if she's still here. Yeah, she's still here. Okay. Yeah, so you're asking about like if it should be 2D, 1D, 3D, right? So like I said, since we're in this context, like in a biological context of like molecules or ions, right, diffusing across a membrane, they can move upwards, downwards, right, in this extracellular fluid and the intracellular fluid. So we're just assuming this case from a biological context that things are moving in 3D, basically, right? Move upwards, downwards, left, right, inwards, outwards, right? Because think about it like if from a cell standpoint, like if this was the cell, here's like your membrane, right? So particles coming in can move inwards or outwards along the z-axis, upwards or downwards along the y-axis, and then left or right along the x-axis, right? So that's how you can think about it. So inwards and outwards outwards from the cell, that's z-axis. Upwards and downwards inside the cell, right? Or in the extracellular fluid, or left and right, right? So once they get into the cell, they move this way or that way to go to different organelles and stuff like that. So that's the idea there, right? That's why, like, you can usually just kind of draw the scenario that they're giving you, and that can help you figure out what equation to use. But yeah, generally from a biological context, like it's going to be this 3D motion. So that's why we use 6dt here. And so they're giving us XRMS is 500 micrometers, right? And we're trying to figure out time, so just isolate for the variable time here. So then XRMS squared is equal to, well, I'll just divide over 6d, and that's equal to the time here, right? So you just take 500 micrometers squared, and then divide by 6 times the diffusion constant that we found earlier, which was the 2.27 times 10 to the negative 9 meters squared per second, right? And that should give us a time of around 18.36 seconds. Oops. There. Make sense for part C? No. So, yeah. So we're using 3 dimensions right here because remember I drew the cell membrane, right? So if we're thinking about this in a biological context, you have the cell membrane, right? Imagine this is like a huge cell. If we blew it up, right? Then here's like your cell membrane, roughly. So you have molecules moving, or these sodium ions moving inwards and outwards from the cell. So that's along the z-axis, right? So that's inwards and outwards. When you have cells or the ions moving upwards and downwards along the y-axis, and then right or left along the x-axis. So you can see there's 3 dimensions: y, z, and x. And so that's why we use root 6 dt as opposed to root 2 dt for 1D motion or root 4 dt for 2D motion. Because we can clearly think about this and see that we're moving inwards and outwards from the cell, upwards and downwards, left and right, right? That's just how we can think or imagine an ion or a particle would move in and out of our cells, right? Yeah, go ahead. Mm-hmm. Well, yeah, that's great. Thank you for bringing that up. Yeah, so if like Anna said, so if they have an like a diffusion problem like this and there's a biological context like she said, then it should be root 6 dt. And if you do that and they count you off, then hold them to that like online homework. So at least you guys have like some kind of proof that like that's what should be going on. So but yeah, like it makes sense honestly too. Like if you think about it from that drawing that I drew, like moving inwards, outwards, upwards, downwards, left and right, like that's naturally how you would probably think an ion or a particle would move. But thank you for bringing that up. And then, so yeah, I made a mistake here. Thank you, Andrews, as well for noticing that. So I put 500 micrometers. We should convert it to SI units, which is 500 times 10 to the negative 6 meters, and then we square that. So my bad. You should make this SI units 500 times 10 to the negative 6 meters. But yeah. And then that gives you, that should give you 18.36 seconds for your time. Let me erase this real quick. Now, for D, if an individual sodium ion was moving in a straight line with a constant speed equal to its RMS speed, how long would it take to make it across the amoeba? 500 micrometers. Explain why this number is different from the time you computed in part C. So if we're moving in a straight line with a constant speed equal to RMS speed, so VRMS is our speed, how long does it take to make it across the amoeba? 500 micrometers. So we're traveling a distance of 500 micrometers. How long does it take us to figure out this distance? Now, this problem, just a kind of a hint, but it's far simpler than maybe you might think. But let me see here. I'll call on someone. Let's see here. Adriana, right? Am I pronouncing that correctly? Do you want to give it a shot? I don't think I've called on you before. No, thanks. Okay, no worries. Let's see here. You can do it. Okay, go ahead. No worries. Yep. Mm-hmm. Yep, exactly. So thinking about it in this perspective is absolutely correct, because you're traveling at a specific speed, right? You're covering a specific distance over a specific time. Well, how long does it take you to cover that distance while you're traveling at that specific speed? So this is just a matter of like really going back to like week 1, week 2, just thinking about what is speed? Okay, it's a distance or displacement traveled over a certain period of time. I traveled 500 micrometers. How long does it take me to travel that distance while I'm traveling at a specific speed, right? And so the speed here that they told you is the VRMS. And so the VRMS was that 579.68 that we determined earlier. And the XRMS that they're giving us here is the 500 micrometers, right? So VRMS is 579.68 meters per second. Is equal to the XRMS, which is 500 micrometers, or let me just go ahead and write it out. 500 times 10 to the negative 6 meters divided by time. Multiply over time, divide over the VRMS. Time is equal to 500 times 10 to the negative 6 meters divided by 579.68 meters per second. And then our time should be 8.63 times 10 to the negative 7 seconds. So that is drastically different than 18.36 seconds, right? This is like, part D is like instant, and part C is relatively a long time, thinking about processes in the body. So why do you think this is so different? This time here is so different. Yeah. Mm-hmm. Yep, that's perfect. Hold up, let me make this a little bit smaller so I can write the explanation. That was perfect. So whoever, or not whoever, those of you who are listening in on this session live, that's 200, 300% correct. But then let me write it out for those who are going to be watching online. So basically, since we are traveling, since we are traveling in a straight line here, there aren't very many molecules colliding with one another, right? However, in part C, right, I think that was part C, the particles are moving at random, so there is potential to collide and bounce off other molecules, right? This random diffusion with collisions with other particles, right, will indicate Brownian motion. And so, not having as many particles moving, or not having as many particles colliding with one another, will help cover the same distance in a shorter amount of time, right? But otherwise, if everything's kind of random, you'll have maybe one particle that's really trying to make it through in a straight line, and it keeps getting bumped and bounced off other particles and stuff like that. So not having as many particles colliding with one another in a straight line will help cover the same distance in a shorter amount of time. This also prevents random changes of direction due to collisions that could extend the amount of time it takes to cover that distance of 500 micrometers, right? But yeah, that's pretty much it. Yeah, they're all like, imagine if everyone was kind of moving like in a single file line, right? It's very organized. Nobody's bumping into each other. No one's going crazy. So it prevents those collisions. It prevents like random motion, like I guess random collisions, changes of direction. That's what I meant. Random changes of direction. And so like imagine if you were a particle, right? And you're moving this way, and you bump into another one, and then you go like backwards essentially, right? Because if you're moving, you bump into another particle, you could go this way, go that way, go this way, whatever. So imagine if you just took a step backwards. Well, then you have to go from let's say if you started off at what? Let's pretend that this is 0 micrometers, right? You started off here, moving along. You at 10 micrometers, you were to be like you collided with another particle, right? And it sends you flying backwards, even past that original point that you were at, maybe at negative 10 micrometers. Well, then now you have to start back from negative 10 and then move onwards, and then maybe you collide somewhere here at like 200 micrometers, and that sends you back a little bit more. So those random changes of direction, those collisions, will extend the amount of time it takes to cover that 500 micrometers. Otherwise, if everyone's moving in a single file line, decrease collisions or lack of collisions in that case, then it helps cover that in a very, very short amount of time. So if you don't have any other particles in the way or any ions in the way or any other molecules in the way, right, the sodium ions will just move from their starting location and cover those 500 micrometers in a shorter amount of time. But yeah. So that's problem 2. Problem 3 is potassium channels. This is where we get into the flux stuff. So it says cell membranes contain potassium channels which can open to allow potassium ions to flow into and out of cells. These channels are approximately cylindrical with a length of 4 nanometers and a diameter of 0.5 nanometers. Consider a cell which has a concentration of potassium ions at 100 millimolars inside the cell and 5 millimolars outside of the cell. When its potassium channel opens, it allows ions to flow out at a net rate of 10 to the 8th ions per second. So first off, in terms of net rate, ions per second, this is our, if you remember from like the lecture slides, this is our N divided by T, right? This would be the number of ions, number of particles, number of molecules per second. That's our flow rate, basically, or our net rate of potassium ion flow, right? Now, we have our diameter, that's 0.5 nanometers, length is 4 nanometers, and they say this thing is approximately cylindrical, right? So if we're looking at a cylinder here, then we can find, for example, values like the area related to it with the diameter and the length that we're given, right? And so now for part A, they're asking us what is the flux of potassium ions when the channel is open. Use the usual coordinates with positive x to the right, and give your answer in units of ions per second times meter squared. So this here, you can see this is our flux. That's the Jx, right? That's our flux. And so you can think of this as literally being the same as our flow, the ions per second, but flow through a specific area, right? It has to be flow through a specific area. So if we think about that, relate it to the equation, right? How do we calculate, what's the equation you use for flux of particles or ions or molecules? Anyone want to chime in about it? Sorry, I didn't make that clear if I was asking a question or not. My bad. Yep, exactly. So for your flux, right, or at least let me write it this way. So our flow, the ions per second, is equal to the flux times the area that we're moving through. And so then, if we want to just figure out the flux, then it would just be the flux is equal to the flow rate times 1 over the area. And that gives us n divided by time divided by area as well. And so you can see here, if this is like ions, right? This is seconds, this is meters squared, then that gives us our flux units, right? So we have this part already. This is our 10 to the 8th ions per second. Now we just have to find the area, right? So the area is not the surface area, right? So this is the tricky part, because they said approximate cylindrical. So you might think, okay, well, it's this surface area, right, of this whole cylinder. So they gave us the length and they gave us the diameter as well, right? That's not the case. When we're looking at flux, it's just the cross-sectional area, right? Just the entrance, just the door, just the gateway, not the mansion that's behind it, not the driveway, not whatever it is, right? So we're just looking at the cross-sectional area. How many ions per second are moving through just this gateway right here, right? So for our area, if it's just the cross-sectional area, it should just be pi r squared. Pi, and then the radius, the diameter here is 0.5 nanometers, right? Well, it's 0.25 nanometers for our radius. So, what do I want to say? Yeah, so 0.25 nanometers, and we square that. That gives us 0.196 nanometers squared. And if you do your conversions and stuff, that should be 1.96 times 10 to the negative 19 meters squared. I'm just skipping the conversions for now, just because I want to make sure I get through the rest of these parts here. But that's our area. Oops, pi r squared. If you just for the sake of clearing this up, so for nanometers, right, 0.25 nanometers, there are what is it? In 1 nanometer, it's 10 to the negative 9 meters, right? And so that you can do that to get your value in meters, and then square it, and then times pi, and then you should get your final value in meters that way. But yeah, that's our area, right? So then we have 10 to the 8th ions per second, right? That's our flow here, multiplied by 1 over the area. And that was just 1.96 times 10 to the negative 19 meters squared, right? So then that gives us a flux of about 5.1 times 10 to the 26 ions per meter squared times seconds, or times, let me write that the other way around, ions per second times meter squared, right? Let me move that upwards, actually. So that's our flux there for part A. Now for part B, they're wanting us to calculate the diffusion constant of the potassium ions moving through the channel in units of micrometers squared per second, right? Now, for diffusion constant, given all these different values here, like we figured out flux already, is there an equation that can help us relate flux to diffusion constant? Yep, exactly. 100% it. So there's your flux times negative of your diffusion constant times the change in your concentration divided by delta x. Delta x is the thickness of the membrane. That's how we define it. Delta x is the thickness of your membrane. So now we just want to figure out the diffusion constant, right? We want to isolate for D. Now we have the flux from earlier. We want to figure out the diffusion constant. How can we figure out the concentration? Right? How do we figure out that concentration there? Or the change in concentration, at least. So for this, right, we have CF minus CI. And so let's see here. So go back to the problem. Consider a cell which has a concentration of potassium ions at 100 millimolars inside the cell and 5 millimolars outside, right? So when the potassium channel opens, it allows ions to flow out, right? So we can basically say that for final here, at least like in terms of like moving outside, right? We want to move outside for the final. And we were initially on the inside, and the initial was 100 millimolars. So our change is going to be negative 95 millimolars there. Right? So that's our delta C, because you can think about like final position, initial position. So if the potassium channels are opening and allowing ions to flow out, well, if there's 100 inside and 5 on the outside and they're flowing out, then our final position would be outside, right? Our initial position would be inside. So we take our final concentration minus our initial concentration to figure out what's the net flow that's going to be, or the change in concentration essentially, right? So we take 5 minus 100 to get negative 95 millimolars. And that tells us that basically there's going to be a change of net flow out of 95 millimolars of this potassium ion, right? Of these potassium ions out from the inside of the cell to the outside of the cell, right? That's a net flow outwards, basically, right? A decrease in concentration from the inside to the outside. So with that, right, for our flux, if we just multiply everything over, right, we have Jx times delta x, our thickness of the membrane, divided by the concentration. That was the negative 95 millimolars. But actually, hold up. Let me. I'll wait for this 1 sec. Hold up. So, and that's our negative D. And since there's going to be a negative sign on the other side, we can just cancel out the D. But actually, hold up. I'll just leave it there for a second just because it might be confusing for those who are going to be watching this later. But there. So for our change in concentration, it's negative 95 millimolars. But for this specific like equation, right, when we're looking at delta C, or just C in general, C should have a unit of like ions per meter cubed, right, or moles per meter cubed, right? And so in this case, if we're looking here, 95 millimolars, well, first of all, millimolars, that would be 0.095 molar, right? As we divide by 1,000, there's 1,000 millimoles in 1 molar, right? So that gives us 0.095 molar, which is moles per liter. And then 1,000 liters is 1 meter cubed, right? So times 1,000 liters divided by meters cubed. And that brings us back up to 95 again, 95 moles per meter cubed. Because remember, the units, the proper SI units for concentration would have to be moles per meter cubed or ions per meter cubed, right? Or particles per meter cubed or whatever, right? So now, though, since we're talking about things in terms of ions, we're not talking about moles, right? We do still have to convert from moles to ions, right? So we take this moles and we just multiply it by Avogadro's number. 1 mole is 6.022 times 10 to the 23rd ions, right? Sound good? So that gives us our final concentration here, the delta C at the bottom, right? That would be the negative 95. There's a net flow outwards, right? Net change of concentration that's negative from inside to the outside of negative 95 moles per meter cubed, and then multiplied by Avogadro's number. I don't have that calculated out, I don't think. So actually, hold up. Let me just calculate it real quick. So negative 95 times the 6.022 times 10 to the 23rd, that should give us around negative 5.72 times 10 to the 25 ions per meter cubed, right? So that gives us the proper final units for our concentration, right? And let me actually rearrange this a little bit so we can clearly see what's going on. So there we have our concentration. We have negative D here. Then we can input our flux and our thickness of the membrane. So the flux was 5.1 times 10 to the 26. I'll just forego the units for now, just so I can save some space. But that's 5.1 times 10 to the 26 ions per second meters squared, right? Now for the thickness of the membrane, this is why I was getting tricky, why I said it was getting tricky at the beginning, because like I said, for the area here, it's going to be cross-sectional area. The reason they gave you this length of the channel, right? This length of the channel, think of that as the thickness of the membrane, the thickness of the channel. It's 4 nanometers in length, 4 nanometers in thickness, right? So that's our delta X, the thickness of the membrane. So 4 nanometers is 4 times 10 to the negative 9 meters for our thickness of the membrane, thickness of the channel. And so you can see here that our negatives will end up canceling out, right? And now we're just solving for D. So once you do all that, your diffusion constant, yeah, go ahead. The X is that's the thickness of the membrane, which is the length that they gave you here. They said the channels are approximately cylindrical with a length of 4 nanometers. The length of the channel is the thickness of the channel, or the thickness of the membrane. So that 4 nanometers is 4 times 10 to the negative 9, and that's your delta X. Does that make sense? But yeah. The weird thing about this, though, is at the very end, you still have the wrong answer, because for your diffusion constant, you're gonna end up with like 3.6 times 10 to the negative 8 meters squared per second, and they want it in micrometers squared per second. So then we unfortunately have to do another round of conversions, right, for our diffusion constant. So once you do this part, right, once you solve this out, you get 3.6 times 10 to the negative 8 meters squared per second, and then you have to convert that to micrometers squared per second. So we know that in 1 micrometer, there are 10 to the negative 6 meters, and if we square that, we have to square the whole thing. 1 micrometers squared, 10 to the negative 6 meters squared, so those meters squared will cancel out, right? So you have to square this whole thing, actually, right? So if you do that, convert to micrometers squared per second, you should get around like 35,000, I think. Yeah, 35,658 micrometers squared per second is what I got. Yeah, go ahead. Yeah, so if this was the negative 95 here, the negatives cancel out because of this negative D there. Yep. No worries. But yeah. Does that make sense for part B? It's a long-winded part there. That was the flux. That was the JX here from part A. Yep. Yep, and that's where we did the 95 times the Avogadro's number, because remember it has to be in ions per meter cubed. Yep. Mm-hmm. Yeah. Yeah. My bad. Yeah, no, I like erased them like midway through just to show that the negatives canceled out, so um but yeah, there should be like a negative like sign here technically. It should be like negative 5.72 and a negative D, and then they cancel out. But yeah. That should be it for part B. Part C is a lot simpler because it's just asking now if it says the cell is at body temperature 310 Kelvin and the radius of potassium ions is 1.33 angstroms. What is the viscosity of the fluid the potassium is diffusing through? So we're looking for viscosity, right? We have values like the diffusion constant, right? We have this diffusion constant now. We have temperature. How can we get viscosity? Yep, kBT, 6 pi viscosity times R. I think this is called the Einstein-Stokes equation. Yeah, that's the one, Einstein-Stokes. But this is, yeah, so excellent. So kBT over 6 pi viscosity times R. So for kB, this is 1.38 times 10 to the negative 23 joules per Kelvin. That's our Boltzmann's constant. T, the temperature is 310 Kelvin. 6 pi viscosity is what we're trying to figure out. We have our diffusion constant, and then our radius is 1.33 angstroms. Does anybody remember what the like conversion factor for an angstrom is? I'm just asking. I mean, I know. I just want to make sure that you guys are up to date on that. Yep. Times 10 to the negative 10. So this would be 1.33 times 10 to the negative 10 meters, right? Now be careful though, because for our diffusion constant, you could use the micrometer squared per second, but then you'd have to convert it back to meters squared per second in order to keep things in SI units. But we already solved actually earlier before we did the conversion for the SI units version, and that was a 3.6 times 10 to the negative 8 meters squared per second. So essentially what you're going to do is rearrange this equation in a way where you solve for viscosity. So you have your viscosity is equal to kBT, right, divided by d 6 pi times r. So then you're left with 1.38 times 10 to the negative 23 joules per Kelvin. That's our Boltzmann's constant, times the temperature, 310 Kelvin, divided by our diffusion constant in meters squared per second. That's our SI units version, 3.6 times 10 to the negative 8 meters squared per second, times 6 pi, and then times the measurement in the radius in SI units, which is 1.33 times 10 to the negative 10 meters, which is the 1.33 angstroms. So if we solve then for viscosity, we should see that it's equal to around 4.74 times 10 to the negative 5 Pascal seconds. 4.7 around, 4.7, 4.8, something like that. But that is part C as well. This homework felt long, especially because of part 1. Just seemed like there was a lot to do. But yeah, go ahead, sorry. Yeah, I can come back to that for sure. Um, but yeah, I mean, this like stuff is just more like math based. The only stuff that kind of requires a little bit more like conceptual understanding is like figuring out how the distribution, how the RMS distances or speeds or whatever change as time progresses, like that part H of problem one, for example. Otherwise, it's mostly like equations and recognizing when to use them and stuff. But it isn't too bad. Are you guys doing fluids next week? Okay, I have a love-hate relationship with fluids. Like fluids in the 131 context um, makes a lot of sense. It's just there's just a lot of equations to look at, a lot of things to keep track of, but it's very equation based. But from a biological perspective, like if you're studying for the MCAT and stuff, man, oh man, is fluids like the concept isn't like difficult to understand. It's just that I don't know, like we're so used to like doing the fluids in the 131 context just with equations and like solving and plugging and chugging and stuff. But then when you think about it in terms of like blood vessels and all that, like it just takes a minute to really apply and think about what's going on. But yeah, it's I don't know how to classify it. It's a decent unit. It's a fair unit, but it does bring back buoyancy, and I don't like buoyancy. Buoyancy can go straight to hell. I don't care that it makes me float. I don't like to swim anyway. But buoyancy can go straight to hell. I'm sorry for any of the people who are watching, but buoyancy is just not my favorite. Buoyancy is just it's just not it for me. It's not hard to understand. It's just like there's something about it. Like the equations look off. They just look annoying to me. They don't look like appealing equations. There's just a lot of pressure and density and stuff, and it just throws me off. Sorry, go ahead, Matthew. That just might be like a rounding issue or something that maybe I just plugged in something wrong somewhere. Um, but like, if you got really close to that, you're fine because I think what they have on the answer key as well is like 3.57 or 3.6. So like we're both kind of off in a sense, but it really just depends on rounding. But if you have all the right steps, then you're good to go. But you said you got 35,609 is what you got. Yeah, then no, that's very very close. So you're good. Yep. Mm-hmm. But yeah, yeah, buoyancy is not my favorite. That's that's the lesson of the day. But yeah, and it's kind of unfortunate too. But well, I guess that well, it's not really unfortunate because it's only election day that you guys are missing. So you don't have lecture on Tuesdays, I don't think. So you're not really missing out on lecture. But um, I don't know. Like I feel like this semester some units seemed to be rushed a little bit. I don't know, but yeah, fluids. I feel like need 2 weeks on fluids, and they only give you one because there's a fat problem on the exam that I remember with fluids. It's like it was like mega thick, like it was just like parts A through F or something like that, and there's just a lot of calculations for it. Actually, just you know what? Let me. Yeah, go ahead. Oh, it's 2 weeks. Oh, well, that's crucial then, because you only got like a week to do it. 1 second here. Let me. Okay, so I'll end the recording now, just for the people who are watching at home. So that's it for the homework and stuff. But yeah, and then Tuesday I'll still have my review session. But that is it.